All right. So which reading is given to 1/10 of a millimeter? All right, let's take the first one, convert that into millimeters. So 10 millimeters make up 1 centimeter. So 3.3 centimeter, let's just be easy about it. Multiply that by 10 on your graph and you're getting 33 millimeters. Is that 1/10 of a millimeter? No, that's just the unit part, right? It's not a fraction of anything. Over here, same thing is going to be 33.1 millimeter. That's definitely 1/10 of a millimeter, because this is 1/10 basically means 1/10, which is up to an accuracy of 0.1 millimeter. If you don't understand the fraction bit, the fraction bit. All right, and similarly this is going to be 33.10 millimeter, and this is 1/100th of a millimeter, and this is 1,000th of a millimeter. So at this point we know our answer. It's gonna be B. A hot air balloon is traveling at a constant velocity and is at a constant height above the ground. The diagram shows the only 4 forces acting on the balloon. Only 4, so X and Y and W, Y and W and X and Z. So it's at a constant speed, right? It's trying to highlight that it's at a constant speed. Constant speed tells you what about acceleration? It's 0. So what's the force acting on it, right? This is 0. So the force is 0. And not just the force, the sum of all forces, the net force is 0 because it's not moving anywhere. It has no acceleration. So all the forces must be cancelling out, hence it's 0. So which statement is correct? W and Y are equal and X and Z are equal. And if it's not, there's no acceleration, W and Y have to be equal and X and Z have to be equal, right? Because changing X won't change its horizontal acceleration because it's completely perpendicular to you, and changing Y won't affect its vertical acceleration, right? So net, upar niche, left, right, they're all cancelling each other out there. So that doesn't mean X is equal to W. It just means W and Y are equal. So the horizontal forces cancel out, and X and Z are equal. The vertical forces are also cancelling out. There are no other forces, so there's no net force, there's no net acceleration. So A is our best bet. And I think the rest are just other permutations. W and Y are equal, but X is greater than Z. Who cares, right? Like, kind of figure it out. There's no change in velocity. It's just there, right? Okay, moving on. The diagram shows a manometer, it's probably called a manometer, containing mercury that is sealed at one end. So there's vacuum and it can go as high as it can, and there you go. What happens to the distance h when the manometer is taken higher up the mountain? So it's at, sea level, and if you take it up, what's going to happen to what's the pressure difference? So the outside, you're decreasing the pressure. So if you decrease it, what's going to happen to this mercury? It's going to climb. Let's say it comes till here, right? And if it rose by a certain height, it's going to fall by a certain height because finite volume, right? Like fixed volume. So it's going to come here, and this is going to, how do I draw that it's gone? So it's not going to be here. So let's get another color. Let's make it white. So it's not going to be here anymore. Should have gone with black. Oh well. Right? All right. So what's happening to the new height? The height is now the h, the difference in height is h new, h old is actually greater than h new, right? So this is h old. It decreases because atmospheric pressure decreases with height. Yeah, okay, height can be confusing, but the higher you go, the atmospheric will decrease and the h will decrease. That makes sense. So correct answer is A. Indeed. Okay, I'm just gonna be OCD about this. A is my favorite letter after all. It decreases because the atmospheric pressure, no, it doesn't increase. And they're just all different permutations. Increase, decrease, increase, increase. So essentially what's going on, it's one of those questions. They're highlighting these. So it's either increase, increase, or decrease, increase. You know, that sort of thing. In this context, decrease and decrease was correct. This is decrease, increase, this is increase, decrease, all permutations of it, and increase, increase. And this was the correct answer. The diagram shows a small car of mass 500 kilogram approaching a hill. It moves up the hill at a constant speed. It went up at a constant speed. The gravitational field acceleration is 10. Ignoring friction, how much work is done in moving the car up? So if there's no friction, all the work done is just literally done on the car in granting it potential energy, right? Right. So all that work is going to be easily calculated by the potential energy is equal to, I should go PE, mgh, and the mass of the car is 500. The gravitational constant is 10, and the height it went up by is also 10, so that's 50,000 joules. And in scientific notation, it's 5.0 times 10 to the power joule. Correct answer is B. The diagram shows air trapped in a flask by a small volume of water in a thin tube. And what happens is, it's in the next part, what happens is the question is saying the small volume of water first goes down to Q, and a few moments later it rises all the way up to R, right? Now I think everyone knows why it's rising up to R, because you heated the heat from the palm is going to expand the air inside, and it's going to push essentially a mercury, right? The mercury thermometer, the heat expands the mercury and it pushes itself out, but over here the water is the visual thing, so air will push this water droplet out, small volume of water. But why does it fall first? What's going to happen is when he touches it, the glass will expand first, and if this expands, the air pressure will lower and this will fall a bit. Then even though it's expanded, the air is going to start expanding, and it's going to start heating up, and that's going to make the droplet rise all the way up to R. So let's check out the answer set. The flask contracts and then the air expands. It's going to expand and expand, less than the flask expands, and then the air expands more than the flask. It expands more than the flask because that's shooting up. And gases will expand more than solids. That's also another giveaway. A parallel beam of light is incident on a thin diverging lens. The focal length of the lens is FL, as shown in the diagram. So you have to predict the ray diagram. So it's pretty straightforward. So whatever light goes through the center of the lens keeps going straight. So let's try drawing that. That's a straight line for me. Okay, good enough. right? I'm at an odd angle, and this light should deviate away from the center parallel axis, right? It's kind of going towards the axis, should kind of deviate, kind of like that, kind of like that. So either two, depending on how extreme you wanna deviate it. I'm gonna actually bet for this guy over here, because it won't match it won't, like if what the focal length does is, if the light was coming in parallel, let's change the color here. If it was coming in parallel, it would kind of deviate this way. So matching this one. So if it's already at an angle coming in, if it's already at an angle, it's gonna deviate just as much, but you know, because it's already bent, it's gonna be a little more horizontal than like that. So let's check the answer set. And we're looking at, let's figure out, this looks fine to me, right? B doesn't have it. This looks fine to me, and this is wrong, this is wrong, right? And for the second set of lights, for the second shade of light, this looks good to me. This looks good to me. This is wrong. A is wrong. B is also wrong, right? I just talked about it's on a horizontal line would deviate in such a way that if you track that line back up, it's gonna touch the focal length. D, that's a bingo. Yeah. Oh, D has the correct line, but yeah, okay, I thought this was correct as well, but it's not. D is out, but C is a bingo, right? That's the correct answer. Which sound wave gets louder and has a pitch that decreases? What would that sound like? It's gonna get louder, so oh, but it's gonna get louder, so yeah, so it's getting louder, but the pitch is decreasing. Okay. I can't do it. Okay. Normally you go higher and increase your energy as well, right? Especially if you're singing. All right, let's one more attempt. Okay, that does it. Okay. Pitch is decreasing, so frequency is going down. Frequency is decreasing and it's getting louder. The amplitude will rise. So amplitude decreases for A, increases for B, decreases for C, and increases for D, right? So amplitude is on the rise here and on the rise here. That's what we want. And we want the pitch to decrease, the frequency to decrease. So how do we check that out? Look at this over here. The frequency seems to be decreasing because this half cycle took 1.5 squares. Now it's taking 1 square. So frequency is decreasing over here. Sorry, increasing, because the wavelength is decreasing. So frequency is actually increasing. So let's figure out the wavelength for all of them, right? That's easier. Then we change it to frequency. Okay. So lambda wavelength is decreasing. For the second one, the opposite is happening, right? It's taking longer wavelength. Wavelength is increasing. Actually, I want to just focus on A, B, and D, right? I can save some time. 1.5, now it's 1. So lambda is also decreasing over here. So frequency is the inverse of lambda. That's the relationship. So this is gonna decrease over here, and frequency is gonna increase over here. They want the frequency to decrease. We want the frequency to decrease. So that's over here. And this. So correct answer is B. Two vertical wires pass at right angles through a piece of cord. There is a large current in each wire in the direction. So this is out of the cord. This is current going into the cord. So if you have the right hand rule, this is my arrow, this is the thumb, right? And the right hand rule, if I place my thumb like that, it's going to tell me that the current is, the fingers are telling me the current is going to go around like that. So it's clockwise, so to speak, with this respect. So if the current is going down into the page, the magnetic field generated is going to be clockwise over here. So let's just erase that and make a magnetic field that's clockwise, like that. And over here the current is out of the page, so if the arrow is pointing towards me, is gonna, yeah, pretty obvious, right? Pretty obvious, like that, right? So the correct answer is, we have C. C is pointing like that. Pretty obvious. Okay, straight, simple stuff. A beam of electrons travels through a vacuum. The beam passes between the poles of a magnet as shown. So the direction of the magnetic field is upwards because it's north to south. That's the direction of the magnetic field. What is the direction of the convectional current, and what is the direction of the magnetic field? Okay, that's interesting. So with respect to these electrons, there's so-called conventional current over here. Let's say you have a wire in which I is flowing this way, right? So that means whatever, this is coming out from the positive end, right? It's coming out from the positive and then going to the negative end. So that's the direction of the current. But the electron, that's conventional current. It's made up, right? But the electrons are actually traveling ulta, backwards, from negative to positive. That's how they're actually flowing. There's actually nothing flowing from positive to negative. It's just a frame of reference. Fun, right? So what would be the conventional current over here? If the electrons are moving this way, there's no wire over here, so it's difficult to think about current that way in your classical way. But you can think of current as on this beam, right? Because the only reason the wire is over here is to control where the current electrons are going. So you make sure electrons don't go anywhere else. They go through the wire, right? Through this wire. Over here, you can control them and make them go straight through a beam. So technically, movement of electrons, that's the current. And your conventional current is highlighting that it's actually against the flow of electrons. So your current is like that, and the direction of the magnetic field. Oh, I thought it was going to ask the motion. But okay. No left-hand rule. Direction of the current is left to right, and magnetic is from bottom to top. Correct answer is now D. All right, a car battery supplies the current in one direction, and the current in the opposite direction recharges the battery. So the car battery is gonna take this current out like that. Like the current is gonna come out like that. So if you want to recharge it, you have to provide current to it like that, right? And that's gonna happen when the current coming from here and here, like the current over here is, if I try to draw a graph, it needs to be on the top side. It's going to be the positive current, right? So over here, the AC current being supplied is going to be positive, then it's going to flip and going to flip the other direction. It's going to actually take the current. It's going to happen. So, but as soon as this flipping, like this current is here, goes, it's going. This current is going through this circuit because the diode allows it. This mighty diode allows the current to go through. It's going. All right, it's gonna stop. So the current is gonna go through like that, but now it won't let it go back, right? It won't, let's say in other words, allow the negative current to go through. So it's gonna stay flat. So this will get a graph that's all positive, kind of like, I should have drawn it over, kind of like a half wave rectified thing. This part won't be there, the missing negative side. So that's going to end up doing what to the battery? It's going to end up charging this battery, right? And this diode is as good as no use because it's in parallel. The current can go through around this way or the other way if it wants to, right? And same with this guy. This would actually allow the current to go through like that, but it won't allow it to charge it. Correct answer is A. A woman runs 2 kilometers x to y in 20 minutes. So she takes 20 minutes from going from x to y and then rests at y. So at y, she's gonna rest for 10 minutes, right? She then takes 10 minutes to run from 1.6 kilometers to see. So she runs and takes another 10 minutes, right? So she traveled 2 kilometers plus 1.6 kilometers. What is the size of her average velocity? Her average velocity. All right, I see. She took a total of, what's her displacement actually? Her displacement is from x, how much was she displaced? She was actually displaced 2.4 kilometers. 2.4, and the total time she took for that displacement was 20 plus 10 plus 10, that's 40. 2.4 over 40. That's 2.4 over 4 is 0.6, 0.06, because it's 40 kilometers per minute. So velocity, right? That's a velocity. Velocity. Right? Not speed. Speed, you would have taken these two values. So the answer is A. Now, in all honesty, that's not really how you think about velocities. This value is more or less useless to anyone doing anything. You don't care for this. So this I deem as a confusing and a stupid question because that's not how you use velocities. There's no point figuring this value out. There's no point to it. Unless you want to figure out like, hey, there's literally, I can't think of any reason why this velocity would come in handy. This is not how velocity. Questions like these will end up confusing. If you try to think about like, why not? It's actually better to calculate her average speed than her average velocity. This is a really bad question. Really, people who don't understand physics made this question. They're like, oh, velocity has to be displacement, so we'll just, make this question up. This is actually a really, not that it's wrong in any way, and that's the problem. This actually is confusing students who are going to take physics later on. It's like what velocity really is. What's the purpose of having velocity? So, yeah, like, I don't know what to say after that. Yeah, they should really not have this question. The diagram shows the distance time graph of a moving object. So it speeds up a lot, then stops moving. So the velocity graph is actually like this, coming straight down, right? Should get better at drawing straight lines. So a ball thrown vertically upwards and falling back down. That distance should actually be, that distance should, because it doesn't highlight that, what's going to happen to the velocity of that ball? Think about it like that. That's easier to explain in a graph. So when you throw it out, velocity is really high, and it goes 0, but it's going to start falling down. So it's going to actually, you know, become negative because the velocities are, so a graph for A kind of looks like this, the velocity graph, kind of like that, right? And you don't see that over here. So yeah. Yep. A car starting from rest, speeding up as it moves away from a traffic signal, but it stops moving. Look at that. It's going to stop moving. It's actually probably a car that's speeding really fast and slows down to a stop, right? The velocity stops. So that makes sense. A drop from a high cliff, falling into the sea below. That would, as soon as it impacts it, that's gonna look like this. The distance for the rock is gonna start moving fast, start moving slow because you just dropped it, but it's gonna accelerate, move fast, then bloop, it's gonna hit water. I think that's an extreme example. It's probably gonna look like this, right? Much more. Well, it could look like this if the distance was high enough, but oh well. A train braking to a halt. That makes sense because earlier I was comparing it to a car. There we go. And let's just, there we go.